something that standing here and releasing open source software has in common. If you mess up, you mess up in public. When we release often and early, there's a huge scope for falling on our faces often and early. I'd like to welcome our final speaker up, who's going to tell us exactly what it means to fail. Paul Fenwick.
Good afternoon, everyone. Good afternoon, everyone. People at the back, can you hear me? Hi, everybody. Right. I'm going to speak very loudly then. Oh, it's working now? Excellent. Excellent. Hi, everyone. I think I'm good. Thanks. Our story today begins in ancient Greece, more than 2,000 years ago. At that time, a device was created, a wonderful device, a device that can tell the position of the sun, the stars, planets, and the moon. This is the world's oldest computer. However, this is also an example of the world's oldest software collaboration, because whilst this was a Greek device, it used the Egyptian calendar for its calculations, input and output. There's also plenty of evidence that the device was modified after it had been created. So this is the world's oldest example of bug fixes and feature creep. In fact, this is a device so rare, so valuable, that it was plundered by the Romans and sent on a ship bound for Rome. Due to a freak accident, that ship sunk off the coast of the island of Antikythera, and there it remained beneath the waves for over 2,000 years. In May 1901, divers recovered this amazing artifact from the ancient world. And in 2006, high-resolution X-ray tomography made a startling discovery. There were more than 2,000 Greek characters inscribed on the outside of the device. This is the world's oldest user documentation. Now, this is a device that encoded its program in hardware, and for the owners of such a device, the largest problems were that of hardware failure, and of course, Romans. In 1947, we were still having those sorts of problems when the first bug was rather famously plucked from the Mark I supercomputer, and that's it pasted into the log book there. It was around this time that people believed that whilst hardware was fallible, software could be made perfect. And this was seen rather tragically in the development in 1983 of the Thirac-25 radiation treatment device. Some of you might have studied this. The Thirac-25 ran on a PDP-11, for those of you who remember those days. And the software safety analysis had this wonderful quote inside it. Errors are caused by faulty hardware components and by soft random errors induced by alpha particles and electromagnetic noise. That's what causes bugs. The device would pick the wrong mode one time in 250 million. And that's a good thing, because if it ever picked the wrong mode, it would invariably give the patient a massive radiation overdose. Also, because software could be made perfect, they'd removed all of the hardware interlocks that existed on the previous versions of the device. Rather tragically, it picked the wrong mode 6 times in 3 years. As we discovered, code means bugs. But the first public bug to really catch the attention of the world was in 1962 with the Mariner 1 space probe. Now, Mariner was supposed to fly to Venus, but it didn't quite get there. The reason for this is that it lost its guidance signal shortly after launch. Now, normally this shouldn't be a problem, because when you build yourself a multi-million-dollar space delivery vehicle, you build it with something called a guidance computer. And a guidance computer means that when you do lose that signal, it still generally goes up. Unfortunately, they discovered there was a bug, although in this case, it was in the spec. The handwritten notes that were handed to the NASA engineers was supposed to contain this term here. That's the smoothed velocity at a given point in time. What they actually contained was this term here, which was the absolute velocity at a given point in time. This meant that normal vibrations you get from travelling through the atmosphere, having a huge rocket launcher attached to you, were considered to be significant. And therefore, the control computer would make even bigger corrections to try and make up for that. And that would make the matter worse. And at this point in my research, I discovered there is something that NASA has in common with evil geniuses. And that is that they're both very fond of self-destruct buttons. The main difference is that if you're an evil genius, you usually have a dashing young spy who presses the self-destruct button. Whereas if you're NASA, you have a range safety officer who essentially does the same task. But wouldn't it be nice if we could learn from these mistakes? And better still, wouldn't it be nice if we had some sort of a metric we could use to compare mistakes, to see which ones were bigger than others? Well, I was at a conference a few years ago, and one of the speakers, Adam Kennedy, said this: "It's possible to make mistakes so large they invalidate your entire worth as a human being." And so that got me wondering, how much is a human actually worth? So I did some rough calculations. Now, I'm from Australia, so I wanted to know how much an Australian was worth. And it's just purely on economic value here. These are very, very simple. Australia's GDP, our sort of productivity per person, is about $40,000 per year. Our lifetime expected is about 8.5 years. You multiply the two together, you get about $3.17 million. So that's the average productivity of somebody over their lifetime. If you can make a mistake more than $3.17 million, you've invalidated a lifetime's worth of effort. So that's going to be our metric. Number of lifetimes of effort lost. So let's look at some failures. Our first failure occurred at AT&T. Back in 1990, they had a wonderful network of long-distance switches. This is a picture of them here. The switches did what you'd expect switches to do. They communicated with each other. And what was actually interesting is how they failed. If a switch had a problem, it would tell all of its neighbours that it had a problem. The neighbours could then remove that switch from the routing table, and the switch could execute some self-test and self-diagnosis code, which would take about 6 seconds. If that succeeded, it would come back up again. And to do that, it completed a 3-way handshake with all of its neighbours. I'm feeling better, are you sure? Yes, I am. AT&T decided that that was too slow, particularly the 3-way handshake. It took far too much time. Every second the switch was down was money and calls being lost. So they changed it. They said that the fault signal still goes out as normal, but now, after the self-fix occurs, rather than going through a 3-way handshake, it'll just make an outgoing call. Because there are so many calls happening, this is much faster than doing the 3-way handshake. January 15th, in 1990, they discovered there was a bug. What could happen is when a switch was making that outgoing call and the neighbouring switch was in the process of updating its routing table, that first switch would make a second outgoing call. The neighbouring switch would say, "Oh, I know about you, you're in my route table." Actually, no, you're not. It would say, "I'm confused." What does the switch do when it gets confused? It goes down. What does it do when it goes down? It tells all of its neighbours. What does it do when it feels better? It crashes all of its neighbours. Very rapidly, 114 switches, which is about half of the entire AT&T network, were rebooting themselves every 6 seconds and then crashing all of their neighbours. 60,000 people were left without telephone service for a period of 9 hours, with an estimated 75 million calls that could not be made. The total cost in lost revenue was $60 million, but that was back in 1990. If you cater for inflation, it's about $94 million, which is around about 30 lifetimes, or almost 2,400 years. The solution to this is rather amusing. What they did is they made all outgoing calls slower, so you could not hit that race condition, which is ironic because they said the situation was too slow to begin with. Now, I am from Australia, so I have a particular joy in picking on New Zealand, which is what I'm going to do now. In New Zealand, TY point 1996, there's an aluminum smelter, which is entirely under computer control. Now, the computers there were designed, programmed and installed by Comalco Australia, who actually do a lot more aluminum smelting than they do in New Zealand. It was in New Year's Eve of 1996 they discovered that there was a bug. Now, you might recall that most years have 365 days, but 1996 was a leap year, which meant it had 366 days. And the computers were just not prepared for this extra day. So all 660 control computers all crash, all at the stroke of midnight. Now New Zealand is about 2 hours ahead of Australia. And rather ironically, 2 hours later, there was an identical crash at the Comalco plant in Tasmania, Australia, for the same reason. Now, one of the things that these control computers did is they handled temperature control. If the cells got too hot, they would burn through the sides. If they got too cold, the aluminium would congeal inside the cells. 5 of the cells completely melted down, despite the fact that they rushed staff in to manually control the temperatures. Now, the cost to replace those was actually relatively cheap. It was about $1 million in total. However, that does not include the repair costs, and it does not include the staff costs of getting everybody to come in on New Year's Eve. The total cost, I don't actually know, but I still have fun picking on New Zealand. But to look at really big failures, it helps to look at space vehicles, because they're big, they're public, they fail spectacularly. And the next one I'm going to pick on is the Ariane 5 from the European Space Agency. The Ariane 5 had a problem in 1996. 37 seconds after it was launched, it veered dramatically off course. Why? Well, they were using a 64-bit floating point number to measure the horizontal distance from the launch position. To give you an idea, that's a number which can be around about that big. What they were doing is they were converting this into a 16-bit integer, which is a number which can be about that big. And just to make it a bit more fun, they disabled all exception handling for that piece of code. Danger, Will Robinson. Danger, danger. Unsurprisingly, there was an arithmetic overflow. Now, for those of you not familiar with arithmetic overflows, when you have a really big number and you add 1 to it, you end up with a really big negative number. This meant that the rocket, when it was supposed to be doing this, thought that it should be doing that. Which is a bug. And then you need this guy to fix it for you. What were they thinking? How do you end up with code like this? Honestly, well, they weren't actually thinking about the Ariane 5. They had reused code from the Ariane 4. Now the important thing is that the Ariane 4 only could travel at 1/5 of the horizontal speed. It simply could not go fast enough to overflow that value. But what about testing? Don't you think that this sort of bug would show up during testing? Well, it did. Absolutely perfectly. Absolutely reproducibly showed up during testing. Do you think they did that before they launched? No. Total cost of the vehicle and its very expensive payload, $370 million US dollars, or almost $500 million after inflation. That's almost 150 lifetimes, or almost 12,000 years of lost productivity. Now back to picking on New Zealand. 1998, the Auckland blackouts. Now you all know where Auckland is. It's where the orcs come from. In the Auckland blackouts, Auckland downtown went without power for 5 weeks. 5 weeks! Now fundamentally this was a case of bad planning. What they had was 150 megawatts worth of load on cables that were only rated to carry 110 megawatts. That's a problem to begin with. Now they had 4 cables and one of those cables failed. Now normally when something like this occurs, you say, oh, one of our cables is down, our network is overloaded, we have to ask people to reduce their power consumption. But they've recently had problems with blackouts, and so that would have caused a lot of bad press. So instead, they didn't tell anyone. There was no attempt to do load reduction whatsoever. So they now had a situation of 150 megawatts on 85 megawatts worth of cables. And a second cable failed. 150 on 60. Now, this is a situation I call management willpower versus and I hate to break it to any of the managers in this room, physics wins every time. So the last 2 cables went out in sympathy. So who was to blame? Well, the official report from management blamed El Nino. The unusual weather conditions caused the ground to shift and move, and that broke the cables. But really, this was a lack of sysadmins, or more correctly, a lack of listening to their sysadmins. Their engineers had known that the cables had been overloaded for quite some time. In fact, back in the 1980s, they were recommending they should replace the cables. The other problem is that the previous failures had not been properly investigated. The cables would go down, they'd patch them up, they'd simply put them back into operation. And of course there was no load limiting. That would have been bad PR. So what was the cost of this? Well, the cost to Mercury Power, who were the company responsible, was only $150 million. That's about 50 lifetimes, around about 4,000 years. The cost to Auckland businesses is big, but unknown. The economic gain by Wellington, the other city in New Zealand, priceless. And this brings us to the curse of the system administrator. The system administrators were not listened to, and this is actually surprisingly common in the system profession. The reason is this: we have a few sysadmins here. Excellent. The problem is that sysadmins tend to be doomsayers. They're always thinking about failure, and they're always saying, what happens if the sky falls down? They're always talking about failure. They say things like, what happens if the disks have a problem? What happens if there's a problem with our power? What happens if the network goes down? The trouble here is that when your system administrators are actually doing their job, everything works fine and it doesn't look like they're doing anything. But provided that the skies don't actually fall down, they are doing something. So do consider listening to your system administrators, at least occasionally. Back to picking on spacecraft, the Mars Climate Orbiter. Who remembers the Mars Climate Orbiter? Yeah. Back in 1998, this is just fantastic. Mars Climate Orbiter, that's an artist's impression of what it was supposed to look like wafting into the upper atmospheres of Mars. What it actually looked like was more similar to this as it plummeted through the atmosphere. Why did that occur? Well, they were using two different ways of measuring force in the code. They were using pounds force and they were using newtons. Now, they're both measures of force, but they're different measurements. And they didn't do any conversion between the two. That's a bug. Rather ironically, the testing budget was cut just before it was launched, and it would have been caught if they'd done end-to-end integration testing. Now, at the same time as this project, there was the Mars lander. Now, the Mars lander was supposed to land on the surface of Mars and do all sorts of interesting measurements. That's an artist's impression of what it was supposed to look like. Here's a picture of it smeared across the surface of Mars. The reason for that is that the landing thruster stopped working a considerable distance away from the ground. Now, the reason for this is that as it travelled through the atmosphere, the landing gear would vibrate because of atmospheric drag. And the control computer said, well, if the landing gear is moving, I must be on the ground. If I'm on the ground, I don't need my rockets anymore. Total cost of this, $327.6 million. 103 lifetimes, 8,300 years. Now, at this point, NASA got smart. NASA realised they were really, really good at smacking spacecraft into the side of Mars. So they designed a probe called Deep Space 2. The only thing you had to do with a Deep Space 2 probe is to hit Mars. Oh, there was an extra one. You had to hit it at more than about 644 kilometres an hour, which is about 400 miles per hour. That's not hard if you drop it from orbit. So they assembled it, they tested it, and then due to a delay in the launch window, it remained in storage for a year. They launched it, they hit Mars, but they got no data back. What do you think wasn't checked?
Batteries.
The batteries. That was relatively cheap, about $30 million, 9 and a bit lifetimes, 742 years. But what's the biggest failure I can find, which I can attribute to software? The biggest one I could find was the North American blackouts that affected the northeast parts of the United States and Canada in 2003. They affected 50 million people. Now, I had a hard time trying to grasp about how big this is, but it's about 2.38 times the population of my entire country. Although it's only about 1/6 of the population of the USA. Now, who was to blame for this? When the power first went out, there was an enormous amount of finger pointing. Well, the finger pointing started with Canada, because they were affected. And they said, we think that this is the fault of New York. The New York grid had been hit by a lightning strike, and that had caused the cascading failures across the network. But it was a sunny day in New York, so it was not a problem there. Canada then said, well, we think it's the fault of a nuclear power plant in Pennsylvania. But the nuclear power plant was still running, even though the distribution network was down. Now, New York is not really one to be blamed by Canada. So New York said, we think it's the fault of those Canadians. But they couldn't come up with a good reason why. Meanwhile, Europe was having a field day. The European press said that the United States is a superpower with a third world electricity grid. This could never happen in Europe. Europe is great. Our power distribution network is fantastic. We will never be without power. No, 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 no. Of course, 6 weeks later in Italy, there was an even bigger blackout. So, what happened? Well, in the northeast grid, outage, it all came down to one power company called First Energy. And they're actually located in Ohio. It started at about 2:15 in the afternoon. And what happened is their alarm system failed. The important thing to realise here is their alarm system failed silent. This meant that it still looked like it was working, but everything said it was green. Everything looked like it was up. It just wasn't updating. 27 minutes later, that box crashes, which is generally considered to be a good thing because a hot spare activated and it lasted a whole 13 minutes before it also failed silent. 11 minutes after that, with the monitoring system not looking at what's going on, one of the very, very large 345 kilovolt lines sags into a tree, the circuit breakers trip, and it goes down. Now, nobody notices this. The reason for that, first of all, is because the alarm system is down, but secondly, it's because when you build yourself a big power distribution network, you have automatic rerouting of load. So when a power line does go down, it doesn't necessarily lose you power. Unfortunately, this meant that the network was now overloaded. So 37 minutes after that, two more of the really big 345 kilovolt lines also go down. And this here was the beginning of the end. But hang on a second, this is one power company. They've got a couple of power plants, a little bit of a distribution network. How do they bring down the entire northeast grid? Isn't there some sort of external monitoring? Well, there is. There's a reliability coordinator, and in this case, the reliability coordinator was the Midwest Independent System Operator, but we'll just call them MISO. Now, they have a piece of software called the State Estimator. What the State Estimator does is it comes up with contingency plans. It runs every 5 minutes and says, here's where we are, here's the worst possible situation, here's what we need to do to avoid that. Much earlier on the day, at 2:15, they started to receive an error from their State Estimator. And the reason they were getting this was from bad data from the neighbour. Now, their software couldn't properly account for this, so they had to stop the automatic updates and go through a manual correction, which took about 45 minutes. Problem solved. It's about lunchtime, so what do the engineers do? They go off for lunch. What did the engineers forget to do? Re-enable those automatic updates. They come back from lunch about 100 minutes later and realise that the updates aren't running. So they turn them back on, but they get another error from the software. Again, it's from bad data, this time from a different neighbour. They disable the updates, and it takes them 84 minutes to diagnose and fix the problem. They finally have MISO debugged. Celebrations are in order. But at this point, they actually look at what's coming out of their software. Not only had 3 of the very large 345 kilovolts lines gone down, but 11 of the smaller 110 kilovolt lines had also gone down. It was the scariest thing imaginable. So, they pick up the phone, they call up First Energy, and they say, hey guys, are you aware that? And at that point, their own power went out. And the cascade of failures swept across the entire grid. But why did this occur? What was the root cause of it? Well, we know what the problem was with MISO. It didn't handle bad data very well. It wasn't very robust. But they didn't have control over the bad data either. But what happened with that alarm system? Well, the alarm system was a multi-threaded application, and it contained a race condition. Specifically, there was a double update problem. You could have 2 threads updating the same piece of data at the same time, and that would corrupt that piece of data. When the display system tried to read it, it would fall into an infinite loop, and it would stop updating. The total cost of the Northeast blackouts was estimated at $6 billion in lost productivity. $6 billion. That's like the entire GDP of Papua New Guinea for a year. So a small country can be wiped out in terms of productivity here. It's 1,892 lifetimes, and because the power blackouts lasted on average for about 32 hours, they were burning productivity at the rate of 1 lifetime per minute. That's how expensive it is to knock out the Northeast grid. So what can we learn from all of these things? Well, one thing that I learned during my research is not to take fashion advice from your power company. But more importantly, you can learn to test your code. Also test your code end to end. That would have fixed up the problem with the Mars orbiter. Also, it seems obvious, but test your code before you launch. Also test your spec. A surprisingly large number of values we saw today were based upon a flawed spec somewhere along the line. And also, listen to your sysadmins occasionally. Some of our other problems would have been fixed there. Also, please think about race conditions. Test for race conditions. And then, because your tests won't find them, think really hard about race conditions more. The nastiest bugs we saw would have been solved by catching those race conditions. Finally, and most importantly, if you are going to deploy code, deploy to New Zealand first.